This is a very peculiar type of math. It's big number math. So some people are getting it. To start out, and what got me going on this track of big math related to learning is just some basic thoughts about information. Now we got way more than 100 people in this room, but let's pretend there are 100 people in this room. And let's pretend that I want to take a picture of every single combination of anybody in this room. In set theory, that's subsets of set. The formula for that is 2 to the n, where n is the number of things, in this case 100. So that means there are 2 to the 100 possible combination of people, of 100 people in this room. Now let's pretend I want to take a picture of every combination of everybody in this room out of just 100 people. Well, that's going to take me, let's see if I can read the number, 40, 169, 423, 537, whatever, 10 to the 22.6 years, which, by the way, is much longer, much longer than the age of the universe. So there isn't even enough time in one universe to do pictures of every combination of people of 100. So just think about that for a second. The enormous complexity of information that arises out of a very small number of components. We have 10 to the 11 neurons in the brain, 10 to the 14 connections of neurons in the brain. A lot of people know that, have been studying it, quibble about the numbers. It's really interesting why it's that big. The number of minutes in 10 billion years is just merely 10 to the 16. We have within our genetic code, probably 30 to 40% of our genetic code is dedicated to metabolism. There's many different possible combinations of viable metabolisms out in the genetic library, 10 to the 30. By the way, if I want to get to 266 people in a room, that's 10 to the 80 combinations. That's getting close to the number of atoms in the universe, which is also 10 to the 80th. The complexity of a chess game is 10 to the 120th. Go even more. And this one is even more interesting, because I've been going back and forth with a researcher in Northwestern some time ago about what's the maximum information capacity of the human brain. We have no idea. You hear a lot of things they don't really know. But in a pure subset of sets theory approach, that number is 2 to the 10 to the 11th, which is a very BFN. So what's the moral of the story? It doesn't take a lot of discrete elements to create hyperastronomical complexity. And that information complexity creates brain complexity. Think about the brain for a second. 20% of our calories go to the brain. Nature puts us asleep in order to care for the brain. Very difficult thing to do. So nature has invested in brains because brains are wildly successful. Brains are incredibly dense, incredibly rich. Why? Because information is even denser and richer. I think we fail to understand the complexity of the problem here. When it comes to instruction, this is a very interesting paper, came out 2013-ish, 14-ish timeframe, I believe. I got to speak to the lead, Ken Koninger, about it. He was just looking at some basic math of the number of combinations in a learning system. If you wanted to have 3 different treatment levels, 15 instructional techniques delivered 2 times in a term. And that alone creates 10 to the 14th number of combinations. Well, that's just the beginning of it. If you wanted to do a treatment per week of a term over 16, that's also a very BFN. What's worse about this for instruction is we don't have a theory of mind. One theory, we got many. There isn't resolution to all of the different theories. And we also don't have much of a means to simulate the problem, unlike our geneticist friends who have ways of computationally simulating what genes do. So the long moral of the story is information complexity creates brain complexity, which also makes learning and learning analytics wickedly hard, in fact, probably far harder than anybody's been confessing.
So really what that ends up meaning is that any big scientific problem starts with trying to solve much smaller and simpler problems. That at the end of the day, we're not going to just all of a sudden come up with the fundamental theory of learning and be able to say that, in fact, this is exactly what we need to do. What we're going to have to be doing is thinking about what people did hundreds of years ago, starting to develop instrumentation, trying to be making hypothesis, making small steps along the way. And so the first step for my institution is really thinking about how do we begin instrumenting the university and collecting data in order to be able to move forward. this slide begins to show one of the early stages of this. And I really have to do a shout out at first to my colleague, John Fritz, and to his, at that time, Blackboard colleague, John Whitmer. They came up with a question: does reading the textbook matter? And if it does, at what point is the latest that you could start reading the textbook and still have a shot at passing a course? Well, that's an interesting problem. We have never been able to really answer that, because when paper textbooks, we couldn't tell when students were reading it. Electronic textbooks, you can begin to answer those sorts of questions. Well, it turns out that for C students, 3 weeks, at least at UMBC, was the key date. And that makes sense when you think about it, because usually it's about the 4th week when we end up having a first exam. If students are waiting until right before the final exam to open the textbook, that's not a good thing, especially if you're a C student. Anyway, as we started to think about answering simple questions like that, what we had to do is build an infrastructure. And so my colleague, Jason Palick, who's down here, Jason's going to be giving a talk at 3 that's going to go over our learning record store that we started to build. But the first thing we did in the upper left is we were just capturing streaming event data. This is caliper data. It's coming from Blackboard, it's coming from VitalSource. Down below, though, is what we realized once we started doing this is that wasn't enough data. We needed data from the SIS. We needed some additional data from VitalSource. And then as we began to look at this, we said, oh, wouldn't this data help us in giving us attendance information or other sorts of things? And so quickly, we ended up seeing that we had to begin loading more and more data. That middle section is where we do all of this now out in AWS. And I want to give a shout out to this community. Jason spent hours talking with people at UC San Diego, with people who were part of Unison, with people at ASU, with other places, and they shared how they were looking at this problem. And from that, we ended up working on a model with AWS to be thinking about how we can do this. What's really unique about the model that we've done is we're doing about 250 million events in the academic year at under $200 a month out in AWS. You can scale these cloud systems very effectively if you take advantage of what the cloud systems do. And so this is an opportunity for higher ed to begin getting into this. And then lastly, what we ended up doing is loading all of that data out into AWS in different data lakes. And what we want to do is make sure we're capturing the raw data, because a lot of times in experiments, what you find is 5 years later, an insight comes up and you want to go back and reprocess data. We want to be able to know we've captured the raw data so that if somebody has an insight and they want to go back and look at data over time, we can do that. So as we think about where we're going in the future, one of the things that came up is early in this process, I had a number of long conversations with Vince. And I have to say, Vince is probably one of the people that I think is a luminary in thinking about this problem. And what Vince was describing is this events-based architecture that was using SAP HANA, and he's going to go over some of that in his next slides. And I was thinking, there's no way that we can do that. That's probably too much for a school that's the size of UMBC. We're only 14,000 students. We probably don't need this. And as we kept going deeper and deeper into the problem, what we began seeing is, yes, everything actually is event-based streams. Whether it's our SIS data, whether it's data that's coming out of other systems, all of this is data that we want to be thinking about that has similarities to learning analytics. And so this idea of streaming event data as a core element is something that really has sort of changed our perspective. And so now we're looking at how all of our data can be ingested as event streams. We're continuing to enrich and load out the AWS environment that we have. And then with some of the technologies that are now available in cloud services, whether it's Snowflake in AWS or Bigtable in Google or other things in Microsoft, I don't know the Microsoft side as well, these cloud services are giving you the capability to create in-memory curated views that are very flexible. And this is what allows you to begin doing interesting problems where you can try to answer questions and potentially even intervene in real time. And so this has been really one of the insights for us, is that we can now think about this new environment not as a learning analytics environment, but as a student success or student analytics environment. So lastly, I just want to do a shout out to my colleagues on the board. So we have colleagues from ACT, Blackboard, and VitalSource who are all on the IMS board. We're doing this study that's looking at emotional skills and learning insights. John Whitmer and John Fritz are really leading this effort, and it's still going on because we haven't finished classes. But this kind of study where you have 4 different vendors all trying to work together is really highlights where there are gaps in some of the ways that we're doing things, where we need to be improving processes. And unless we're doing some of these hard kinds of problems, we're not going to fix where we have issues so that everyone can take advantage of this. And this is what I think is one of the benefits of this community is that we can come together and really be able to sort of help advance all of our efforts by sharing what we do.
Thank you. How much time do I have left? An hour?
8.
No, I had taught for years in the 3-hour format for adult learners, so I could go forever, but I'll keep it short. A lot of what this is leading to is sort of some new rules for how to think about data platform architecture in these areas. I'm going to list them here very quickly. The article is actually available at EDUCAUSE Review now. But the 6 rules are simple. One is everything's a verb. Just as Jack was saying about event data, you can treat all nouns as literally changes to the noun and a verb, and that's the way we do it. Things like streams, replayable log, eventual consistency models. For any data wonks out there, this will be familiar. A phrase we use is express maximum semantic complexity. It's a very fancy way of saying bring all data in at the lowest level of granularity, whether you need it or not. Sort of like putting in electrical cables in your house before you put the walls up. A lot easier and cheaper to do. This one is very hard for folks. Build provisionally. We don't have to build forever. We can build for what we need now, today, and we can adapt it and evolve it over time. So how do you create an agile environment here versus a permanent sort of Greek architecture building? This is an important one, designed for the speed of thought. If the analytical environment works at the speed of human, what we're doing within our brains, the environment now gets pleasing. How many of you have worked in analytical environments where you click and you wait 7 seconds? Yeah, you start to want to do this to your wrists and get a cup of coffee and hand it off to somebody else. When that click comes back less than a second, typically that half-second range, now you get a little addicted. Waste is good in this environment, meaning you can explode the data. You can have duplicate forms of the data. These environments are heavily deduped. That's okay. Last one here, and probably the most challenging, democratize the data. I said that once, and somebody snarked, that won't happen here. We can't democratize the data. It's too threatening. Baloney. This is a complex problem. We need information in the hands of as many instructors, advisors, and people as we can who help our students. I'm going to give you 2 quick views here in the last few minutes I got. This sets up an interesting proposition in that we can now consider artificial intelligence and machine learning as part of the ecosystem within our environments in our institutions. Now for vendors who are doing the same, I will call it collaborative AI. You have AI, we have AI, our AI got to meet for lunch and know how to talk to each other. So we've invested in this streaming API architecture that I described and Jack certainly referenced. We have our next generation data warehouse, which is a combination of data lake and data warehouse. I'll show you in a little bit. But we're now starting to architect how would we run 20, 30, 50, 200, several hundred machine learning algorithms live on data that's flowing constantly. And then more importantly, how do we create a machine learning platform that will need to develop those models? This is not your parents' BI, okay? This is new school BI in which it's much more dynamic. It's like tires. You got tires on a car, you're gonna be changing them while the car is running. So you gotta change those tires, your machine learning models while the car is running. There's a great book out there, Machine Learning Logistics. It's an ebook, you can get it online, coming out of a company called MapR. The architect for that solution turned me on to that idea. Finally, another version of this architecture is perhaps a little more practical here for the crowd. And this describes exactly what we're building here at San Diego. So we have different source systems to student data, but not just student data, we can go well beyond that. But even in our student realm, we've got lots of different sources of data, and that's in your upper left-hand corner there. That data flows through our IPaaS, that's IPaaS, that's our term for describing how we're gonna bring streaming data into these environments. That for us is Kafka, NiFi, and WSO2 API Manager, all open source tools, cheap and free. We are using Informatica Cloud for old school ETL for things that still need that. And from there, the data flows into essentially a data lake. For us, it's one big activity table. It's a variable structure, variable length record structure of old, way back when. It's similar to the IBM Pile file, although it's stored in relational table form. And we add ad nauseum to that table. That table can hold tens of millions, hundreds of millions of rows without problem. We have tiering on that, so we can tier it down to very low-cost disk and keep in memory rather parsimonious. From there, we create essentially 3 to 4 layers of curated views. These are just merely SQL statements that call each other. And we do that freely and sort of promiscuously across the environment to render a curated view that's perfect for an analytical sort of vignette or analytical purpose. And the idea behind these curated views is that the analyst doesn't have to worry about joining data. They merely have to use the data as is without a lot of work. So we're trying to be extremely analyst friendly. From here, tools like Tableau, Cognos, and other BI tools can easily be put on top of that and displayed. Part of that in the middle, though, is what we still have yet to architect at San Diego, but we will, is a machine learning platform where the data flowing through Apache can be forked into this machine learning platform for real-time analysis of the stream of data as it's flowing through the environment and potentially messaging out to other systems to take action. Ideally, this can also serve as a way for near real-time, in the middle of a learning activity interaction with the learner, almost a quasi-adaptive learning sort of environment. But we understand there are places in the world that are looking at cloud-to-cloud, real-time adaptive learning environments with this type of data flow in mind. Finally, there's a little thing here we call Hierarchy Manager. In all of this work, the teams that do this, sort of struggle with how do we define the data. So standards like Caliper come in extremely handy because it provides a definition for looking at the data. Extendability of the standard is now there, so we can extend that. In fact, we've done that. We've taken the Caliper standard, we've added in hundreds and hundreds and hundreds of events related to the breadth of student systems that we have. And then we've got a place to manage that hierarchy of information. We have to conform those hierarchies reasonably well in order to get immediate use of the data. And so I think the need to manage your taxonomy, your metadata, becomes even more paramount in this environment. So we're pretty far in construction of this, certainly in our Student Activity Hub, which is our student success platform. We're about ready to start ingesting Canvas events and other events from our co-curricular record, our advising systems, and others, and starting to deploy analytical views for all of the above. We've got mobile messaging hooked up into this architecture, and now we're thinking about the design of our machine learning platform based upon TensorFlow and GPU and FPGA architectures. Technical, I know, for folks here, but I know there's some technical people in the room, especially among the vendor community. So thank you. I have a minute left.
Oh, I get the last minute.
Yeah.
So as we've talked about this, what was really interesting to me was as a number of us were talking back in late summer and early fall, we were first thinking, what UCSD is doing is just so far out there. We'll never need that, or we'll never get to that level. And as we started looking at the problem space, Vince has been looking at this problem space for a decade or longer. What we began to see is, yes, in fact, this makes a lot of sense. That this model for how we're thinking about it is one that we can do. And what was really helpful is again, talking with a variety of people through the community, some of the insights that came out about what Snowflake could do in our environment, or if you're in a Google environment, what Bigtable might be able to do for you. And so I think that one of the things that we're hoping to see come out of this is we're going to get a community together who want to be talking about how we can be building this analytics environment and sharing what we're doing. One of the things that also was interesting is we've talked about a data model. I know Vince's is SEDS-like. It's turning out. Ours is SEDS-like. I've seen posts from the Unison community. It's SEDS-like. You know, we have an opportunity to sort of be thinking about how we come together and how we collectively work on trying to advance analytics infrastructure so that we can do the kind of experiments that are going to help us begin to take those first steps towards understanding the complexity that Vince laid out. The good news is we probably all have a long job ahead of us, so it'll keep us employed for quite a while. But anyway, thank you all, and I appreciate this.
Yeah.